Okay, good morning everyone. Welcome to the last day of PDC. My name's Tim Harris and I'm over from Microsoft Research in Cambridge to talk about some of the work that we've been doing on concurrent programming. Now, throughout this talk you'll see that the slides are this slightly garish red background, and that's just to remind us and people seeing the slide deck afterwards that this is speculative work that we're doing in research, rather than particular features that Microsoft has committed to shipping in any particular product. But having said that, and as I'll come back at the end, a lot of the work that I'm talking about has got prototype versions available for download, and of course research papers about the algorithms and ideas involved. So although this is all somewhat speculative, I hope there's some things that concretely you can take away from this session and think about whether these kind of ideas are going to help in the kind of programming challenges that you're seeing. So just to start, I'm sure that we're all aware that advances in computer hardware have over the years driven massive benefits in terms of the performance of computer software. In one particular example that I'm sure has come across during this PDC is the benefits from the graphics hardware and acceleration there in delivering the kind of rich user interfaces that we see nowadays. And the motivation for the work in this talk is the emergence of a new area where hardware is providing new facilities that can be used to improve software performance. And this is the area of multiprocessor and multi-core CPUs, and the transition of these from being a kind of just server-side facility on something that's used for scientific workloads into something that's available on a commodity basis on desktop machines and possibly in the future even on notebooks. And now, developing software that can make use of multiple processors, as I said, provides new opportunities for performance improvements, but it also introduces new challenges in actually getting the best out of that. And during PDC, we've had a series of sessions about some aspects of concurrent programming and what can be done to try and benefit from this hardware. You may have seen Jan Gray and Joe Duffy's talks during the sessions on the tools and techniques that are available on the current Microsoft platform for concurrent programming, and some of the details about how concurrency is used inside the platform, whether your application uses it or not. And so this session is dealing with the last of these bullets, the techniques that we're investigating for future languages, for future tools, to see what we can do beyond the facilities that are already available in the platform today. Now, as a motivating example, and to illustrate the kind of challenges that arise when programming for multiprocessor machines, we could think about an example like this, with a group of threads communicating through a shared queue. And so this could be perhaps in a server application with threads on the left pulling work items out from network connections, putting them into a queue, and then a thread on the right perhaps implementing some kind of thread pool, pulling those work items out of the queue, processing them, and delivering some kind of result as a result of that. Now, if you implemented this queue just directly in the way that you would for a single-threaded system, then there's obviously lots of problems if you just use that basic queue in a multi-threaded machine. Because we could have two threads working on the queue at the same time, updating the same references, and just leading it to get into a jumbled mess because there's no coordination between them. And so the basic solution to make that kind of data structure safe for multi-threaded use is to introduce some locking, as Jan described earlier in the week. So one way this could be done would be to associate a lock with the entire queue structure. When you want to put data into the queue, you acquire the lock. When you finish that update to the queue, you release the lock. And so that makes sure that everyone's work is serialized, that we don't have the queue getting inconsistent. But that's not going to scale well to multiprocessor machines, because it means that only one thread at a time can be working on the queue. And you can see that if the queue had 1 million entries in it, then we could actually quite safely have threads pushing and popping items on the left-hand end of the queue and at the same time as pushing and popping on the right, they're working on different parts of the data structure, and so there's no real need for them to contend for the same lock. So we could try to improve the queue, and instead of having one lock, we could have two locks. One protects the left-hand end of the queue, the other lock protects the right-hand end. And this gives some better scalability, because we can have threads working on the two ends of the queue independently and possibly get a factor of 2 improvement in the actual utilization of this structure. But there's problems in using locks like that. One is that the code is simply much more complex if you want to design it to use 2 locks and to be correct. And a reason for that is there's a risk of deadlock. If you think about the case where the queue has just one item left in it, and one thread is working on the left-hand end wanting to pop an item off the queue, and the second thread is working on the right wanting to take that same item out, then we need to work out whether it goes out of the left-hand end or the right-hand end. And it's easy to design a queue that looks correct, but where perhaps the thread on the left takes one lock, the thread on the right takes another, and then they see the queue as almost empty and need to work out who gets the last item, and they're both stuck, possibly waiting for the lock that the other thread has. A more subtle problem with this kind of locking is that the system isn't composable. So if we suppose that there's a whole bunch of queues in the system, and a thread wants to take an item off one queue and put the item onto another queue without other threads being able to see the item in transit in between, then we can't actually build a correct solution to that problem out of a correct solution for these simple queues. Because we need some way of atomically locking both of the queues at the same time to prevent someone else seeing the item missing but not yet reinserted. And even if we've built all of this careful, fine-grained locking to allow good concurrency in one queue, we really have to throw that away and build some new locking further out in the client code calling the queue if we want to do operations that span multiple queues. And then one final problem with this kind of queue structure with locks is it still doesn't actually scale up quite as well as it could. And you could think about a case where the system has 1 million threads all trying to communicate through queues, some pushing items on the left, some popping on the right. And this system is still going to only allow one thread at a time to work on either end. It's still better than a system with only one lock, but it wouldn't allow, say, groups of those 1 million threads to be paired up at the same time and exchange data. We've still got a lot of needless serialization. And so these kinds of challenges are the ones that the research projects I'll talk about are trying to address. They try to make it easier to write code using locks that's correct, and then they try to design techniques that make it easier to write composable and highly scalable structures without the extra complexity that would come about by trying to do that by hand using conventional facilities. Now, the talk is going to be described in 3 sections. And the first strand is looking in the fairly near term at what extra tools we can develop to make it easier to detect bugs in code using locks. So, for example, to detect if there's code that is using locks inconsistently, leading to race conditions. The second strand is looking a bit further out at what kind of additional features could be added to a language to document how locks are used, and to mean that the compiler can detect at compile time that there's some problem with the concurrency control in a program, rather than having to leave that till runtime and all of the problems of non-determinism that make it hard to debug concurrent code. And then the final strand of this talk is looking at, further out, what new language features could completely replace locks. And we'll see some exciting results there that really fit in nicely with the ideas that you might have heard Jim Johnson talking about in the system.transactions namespace yesterday afternoon. So we'll look first of all at this first strand, tools for detecting concurrency bugs at runtime. And the tool that we've got here is a system called Racetrack. And this is a modified version of the CLR, where you can run an unmodified version of your application over it. And the Racetrack runtime instruments the application, instruments where it's locking and unlocking data, and tries to identify where there's inconsistency in how the application is using locks to protect shared state. And the benefits of this approach in Racetrack is that it will work with existing applications. You don't need to take the application code and annotate it to describe how it uses locks. And you don't need any kind of pre-processing on the application. You can run it on code simply as an assembly. And as Racetrack runs, and as we'll see in some examples later on, it studies how the program is locking and unlocking, and will issue warnings showing which data structures may not be being controlled correctly, and it'll show you the actual line numbers in the source code where some of those problems occur. So I'll first of all look at the basic algorithm that Racetrack uses to try and work out if the program is using locks correctly. And the idea here is that we assume that the program is consistent in how it controls access to shared data. So for each piece of shared data that the program accesses from multiple threads, we expect that there's a lock that the runtime can identify that must be held whenever that shared data is accessed. And as the program runs, we monitor how it acquires and releases locks, and we issue a warning if we find that there's some shared data where there isn't a lock that consistently protects it. So in this example here, we're going to have a group of threads accessing these two fields on the right, value and next. And as they access those fields, we're going to update a set of candidate locks that are the system's current best guess at which locks are protecting that shared data. So we have a first thread, T1, that currently holds locks A, B, and C, and it runs for a while and accesses the value field. Now at this point, the candidate set of locks for the value field is initialized to A, B, and C. We don't know whether it's A or B or C, or maybe some combination of these that's needed to protect value. But we know that it's at least one of those three and not some unrelated log. Now thread 1 continues, and perhaps thread 2 runs, and it's now holding locks C and D. And it accesses the next field, makes an update to that. And so we know that the next field is protected by either lock C or by lock D. And you can see here that we have to do this tracking on a per field basis because we might have data structures with complicated locking patterns, perhaps a linked list where one lock protects the list nodes itself and a second lock protects the actual data in them. So it's important we keep track of this information for the two fields. Now thread 2 keeps running, and it also accesses the value field holding locks C and D. And at this time, the Racetrack runtime knows that it can't have been lock A or lock B that protected the value field because T2, the second thread, didn't hold those locks when it accessed it. So we've narrowed down the set of candidate locks for that value field. And as the system runs, perhaps thread 3 comes along and just holding lock D accesses the value field. And this is now the time that Racetrack can issue a warning because it's exhausted all of the possibilities in that set of candidate locks. And so we know that there's no consistent way that concurrency control could have been enforced. And we'll get a warning saying, thread 3 accessed that field, here's the stack trace of it, can you go and look at the program and check whether that's actually a genuine error or whether whether it's a false positive. Now here's an example taken from running Racetrack on an earlier version of MS Corelib, showing a potential race that it detected in the way that remoting was implemented. And the output here from Racetrack shows the stack trace of a thread and a warning that was issued when it executed a store field MSIL instruction writing to a particular offset in a given object. And the warning here relates to a line in remoting attributes, and we get the line number and the position in that source file. Now looking into the source file, we've got a set of two methods here that are tracking some of the information about a remoted method. The first method with the circles highlighted in it is one way, and that's used to work out if it's a one-way invocation or if it's an ordinary synchronous method call. And you can see inside is one way that we're accessing a flags field. In the first circle, we test it against some bitmap, and then in the second circle, we do a read, modify, write to set a bit in the flags field. And that should suggest that there's some concurrency problem here, because there's no mention of locking or synchronization in this class, and yet we've got all of these accesses to a field that are not going to be made atomic by the runtime system. We're reading, modifying, writing, and a second access by a thread, say in the runtime type method at the bottom, also makes those kind of read, modify, writes. So it would be a classic example of a race condition. Now, in this case, it's actually fairly difficult to exercise this race condition at runtime. We need about 3 threads to do so. And that illustrates why tools like Racetrack are valuable, because it would be really hard to actually see this race bite to you at runtime. You'd probably need hours of testing to see it. And yet, running it in Racetrack, even if we don't actually have the race occur, the monitoring that it does is enough to show that the locking is inconsistent and that there's a problem to be fixed. So in this case, we could get the race if thread 1 gets halfway through return type and it's preempted just after it's read the flags field and just before it writes to the flags field. Then we switch to thread 2 that calls is one way and goes partway through that method, reading the flags and then updating them to set result one way and checked one way. Then we have thread 3, call is one way, see that the checked flag is set, and then be preempted. Then at that point we have to switch to T1, continue to the end of the method, back to T3, and go all the way through. And only then do we actually see the race condition bite. We get to the end of T3, and because T1 has stomped on the flags field and lost the result one-way setting, then we have T3 incorrectly see that result one way is clear, and we've given the wrong information about that method. So it's a subtle race condition, and one that must have escaped many hours of testing and code inspection, but one where the monitoring that Racetrack does is able to identify that this problem exists. I've just got a note here. There's overflow set up in room 511B if anyone without a seat here wants to go over to that room. Okay, now, if you've been thinking about some possible scenarios of how Racetrack could be used in your applications, you might have spotted that there's a lot of weaknesses in this basic algorithm, because there's a lot of things that an application can do that are actually thread safe, but that won't be that will be picked up by this locking analysis as being incorrect. So, for example, a thread might allocate an object, initialize all its fields, and then, without having any locks on it during the initialization, then make it shared, and a second thread accesses those fields with a lock. Racetrack, with this basic algorithm, would report that as a bug, because we've got the fields accessed without locking in one place and with locking in another. So we actually have a number of extensions to Racetrack to identify that kind of structure of an application and to avoid issuing false positives. The key algorithm that we use to do that is to divide threads execution into chunks based on how the threads communicate with each other, and to only issue warnings if we see inconsistencies between chunks that might be parallel with each other. So, for example, if thread 1 runs for a while and then spawns a second thread, it calls thread start and creates thread 2, then we know that if there's inconsistent locking between A and B, or between A and D, then there's no problem, because those sets of thread chunks can't execute in parallel. We only need to report errors if there's races between B and D. And similarly, as threads run, if we get a third thread, then we don't need to report errors between B and E, but we might need to report errors relating to locking for C and D. And so this structure of tracking how threads are created and how threads communicate through primitives like joining and through queuing items on thread pools means we can detect a lot of the common code structures that eliminate the need for locking and therefore eliminate the generation of false positives in the Racetrack output. Now, I can give you some details later on about some other examples of Racetrack and the algorithms it uses and the ways that we really make it home in on genuine errors rather than false positives. Now, the second stage of this talk is looking at what we could do in languages to try and avoid the need for tracking races at runtime. And so instead of having to monitor things with a system like racetrack, we want the compiler to pick up, when we compile a program, that it might have race conditions in it. So we can ship it and know that there aren't any problems. It's not just that we didn't test it thoroughly enough. We can be certain that it doesn't have races, just as we can be certain that it doesn't have type errors. The intuition for these extensions is really that systems like racetrack had to infer at runtime how the programmer was using locks. And so we can provide mechanisms for the programmer to document in their source code how locking is supposed to be being used, and then use those annotations to identify where there's inconsistencies. And this is coming from a project called Spec Sharp that extends the C# language with what's known as a design by contract method. And what design by contract means is that the source code is annotated with details about what a called method guarantees to do and what assumptions it makes about its caller. So this is actually a much more general method than just dealing with locking. It lets us deal with, say, specifying pre- and post conditions on a method, saying that the length passed into a constructor for a list must be a positive integer rather than just any integer. Or we can have conditions that say when we've called a method, the abstract state of an object that it's been called on has been updated in some certain way. But the focus in this talk is on what we do in Spec Sharp to control locking. And this is based on notions of ownership, where we aggregate together groups of objects that are supposed to be controlled by the same lock. And by making that ownership relationship explicit in the source code, we can make sure that those objects are only accessed when the owning object has been locked. I've got an example on the next slide that illustrates that graphically. The result of this method is that we can be sure that the locks that protect the data are correctly acquired. And therefore, because whenever we're accessing shared data, we know it's correctly locked, we can reason about what the program is going to do as if it was single-threaded, because we know there aren't going to be unexpected interactions and races between different threads using the shared data. So, to illustrate this idea of ownership, I'll use an example of a stack. And we've got a set of nodes that make up the stack going across the top of the slide. And then at each position in the stack, there's some objects that have been pushed onto it. So we've got one node in the middle and then a kind of tree structure that's been pushed onto the stack twice. Now, the different color arrows indicate these distinctions between owning and non-owning references. The thick red arrows show where there's an ownership relationship, and the ordinary thin arrows show where there's just an ordinary object reference. And when it comes down to locking, what this means is that when we acquire a lock on an object at the top of one of these trees of red arrows, then we implicitly acquire exclusive access to all of the owned objects that are reachable from it. So if a thread locks the top of the stack, then that grants it access to the whole spine of stack nodes going across the slide. And when a thread, for example, thread 1 over on the left, has a lock on one of these data items that's going to be pushed into the stack, then it's got access to both of those two items with only one lock acquired. Now, you can see the importance of still distinguishing owning from non-owning references, because non-owning references let us partition the heap up into these different ownership domains, so that we can have one thread perhaps owning the contents of the stack on the right there, and another thread owning the stack as it's manipulating it. So if we think through what would happen if thread 1 wants to push items onto the stack, it initially creates the items that it wants, and because those are created thread locally, it has exclusive ownership of them. Then thread 1 wants to acquire access to the stack to make sure that no one else is going to work on it concurrently. So it does an acquire operation on the top of stack, and that means that that entire group of objects is now owned by thread 1. The thread can then manipulate the pointers within the stack and within the objects that it owns knowing that no one else is interfering with it, it creates a new stack node and links in the data that it wants to push. And then thread 1 can release ownership of the two groups of objects, making them available to other threads. So the programming model here, in some ways, is very familiar because we're dealing with locking and object graphs. But by adding this slight addition of owning references, we allow the programmer to document the structure of those graphs in a bit more detail and to distinguish exactly what data is acquired when a thread acquires a lock on one particular data object. I've got a second example here from Spec Sharp looking at some source code and illustrating the extensions that the design by contract methodology adds. The example here is a shared counter where we've got an increment method and then a second method that's supposed to increment the counter by 2 rather than just by 1. The Spec Sharp additions are these bold words in the kind of yellow font. And looking down through the lines of counter, the first annotations are on the increment method, saying that when inc is called, it requires that that object is owned by the calling thread. So owner is a kind of ghost variable that the Spec Sharp system uses to refer to the current owner of the lock on the object or on the aggregate object that forms part of. So this is saying that there's a contract that requires whoever calls inc to already have got a lock on it. The ensures annotation there is documenting the behavior of inc. It's saying that once the method has been called, the contents of the count field of that counter are going to be 1 higher than the value before it was called. So this is illustrating the use of more general contracts than just lock annotations. Atomic inc by 2 shows a place where the increment method is being called. And you can see we've got 2 calls there, and they're wrapped in an acquire block, which is the Spec Sharp equivalent of a locked region. So we acquire a lock on this, make the 2 calls under increment, and then assert that the counter value really has gone up by 2. And because we've got this extra information on the counter class, saying about how locks are needed and saying that 1 call to increment increases the counter by 2, we're able to check at compile time that, first of all, we do actually hold the locks when calling inc, and that assertion can also be checked at compile time because we can see that they're making 2 calls. We hold the lock exclusively throughout that region so no one else can interfere with the counter, and so we can be certain that inc by 2 really has the effect of an increment by 2 rather than allowing any interference from concurrent threads. And the example at the bottom just shows how a counter class could be instantiated and used. We allocate it thread locally, then invoke a special share method that says this is now opened up to public access and further access has to be mediated by acquiring locks. And then we create threads in the normal way, executing the inc by 2 statements. So this gives some flavor of what we can do in Spec Sharp to do disciplined locking with fairly straightforward extensions to current programming models. And if you go to the Microsoft Research web pages, I've got some references later on, there's an alpha version of Spec Sharp that you can download and see some of these features. So the final section of the talk is looking at what we can do in the longer term, going beyond locks as an abstraction for concurrent programming. And this is really aiming to provide a number of features. As we'll see in some of the results here, it stands to provide good scalability on multiprocessor and multi-core machines beyond what's easy to achieve using locks. And it also tries to provide improved or more robust software engineering techniques so that we don't have to use the kind of tools like Racetrack to detect races at runtime, or we don't have to have quite as much annotation as Spec Sharp has to a document locking at compile time. Now, the first idea that I'm going to talk about here is one that might be familiar if you've been to Jim Johnson's talk on the system.transactions namespace. And that is that we can view the heap of that the program is accessing just as another data structure that can form part of a transaction. Just as a transaction can access database data, as it can access files in NTFS, and as it can now access the registry, we can extend those ideas to have these very kind of wide transactions that encompass the full range of state that the application is accessing. And this is a very straightforward programming model. We don't need to say whether the code needs to acquire locks or release locks. That's really pushed down into the implementation of the transaction system in a modified version of the runtime environment. So, as an example, if we had two methods, withdraw and deposit, that were manipulating some kind of in-memory representation of a bank account, then we can just wrap those in an atomic block with these new language features. And that combination of methods will run as if it's not being interrupted by other threads. And we haven't had to do anything special when writing withdraw and deposit to make this facility available to them. They're just ordinary methods written with the ordinary features of the language. We could be calling, say, operations on the hash table taken from the standard libraries. We could be calling existing code that we wrote for an old single-threaded application, and we can just reuse that in a transaction alongside accesses to all the other kinds of transactable state that the system takes care of. So I hope that makes clear the kind of software engineering benefits from using transactional memory, from using atomic blocks for programming multiprocessor machines. But there's an important other benefit of this, which is scalability. Because we're not documenting which locks to acquire and release, the system's able to resolve conflicts on a much finer granularity than it normally would with locking. So going back to that example I had at the start of a shared queue with push and pop operations on both ends, if it's built using transactional memory, then the push and pop on the two ends will naturally work in parallel with each other because contention is detected on a per field basis or on a per object basis. And so if the two ends operations don't touch the same objects, then they'll be able to execute in parallel. And better than that, if we had other read-only operations on the queue, so peeking the next item on one of the ends without updating it, then multiple threads can actually run that read operation in parallel, as long as no one is making a conflicting update. So we get all the benefits that would happen from a carefully designed, fine-grained locking design, but with much easier ease of programming than would be necessary to get that kind of well-engineered lock-based system. And we also get composability, because we could take this code to do, say, withdraw and deposit, wrap that in a larger atomic block, and do some other interrelated operations on other data structures. And just as with system.transactions, we're able to glue together correct small pieces of code into correct larger pieces and get better code reuse. So we'll look next at a quick example of how transactional memory works. And I can give you some more references at the end of the talk if you want to follow up the exact low-level details here. So the example is dequeuing an item. And we've got a number of threads that are going to try to take items off this queue from the left and right ends of it. The basic implementation technique that transactional memory works with is that as the thread runs inside an atomic block, it builds up a log of all of the memory accesses that it's made, whether those are read accesses, whether they're updates. If they're updates, what value it wants to write into memory. And then when it gets to the end of the atomic block, these thread logs of the transaction can be used to actually commit that to the real state of the heap, alongside any other transacted operations that might have occurred, like a database access. So if thread 1 is doing pop left, trying to take the node B item off the list, then its transaction log starts up with an empty list of reads and updates, and it proceeds to read from the queue's head field, to read from the next pointer from node A and to read from node B the value that it's wanting to take out of the queue. And so as it does those reads, you can see it's building up a log of all of those addresses that it's accessed. And the red values are marked in the shaded blocks in the middle. Now we do the actual updates necessary for pop left. We update the head of the queue to refer to node B. We update the previous field of that node to null it out to make it the new sentinel node on the left. And we update the value again to make it into the new sentinel node for the queue. And at the same time as that thread is running, we could have a second thread trying to do an operation that is safe to run in parallel on the other end of the queue. So it's built up a list of the reads necessary to do pop right, the updates that are necessary. And then when these threads get to the end of the atomic blocks, the runtime system takes this list of reads and updates, and basically by using algorithms built over the interlocked compare-exchange operations that the runtime system and the hardware supports, it makes sure that all of these memory accesses are performed as a single atomic step, so that as far as the programmer is concerned, the pop left or the pop right operation occurs without any interruption from concurrent threads. Now, it's important to see that although we've got this extra step of putting in logging of all of the memory accesses, all the memory updates that are made, this is something that happens transparently as far as the program is concerned. This is something that's introduced in the transactional memory implementation inside the runtime system. So the programmer can use all the standard library features, and the runtime translates it into these logging operations and the final transactional commit using interlocked instructions. So how does this perform? Well, the benchmark I've got here is a simple micro benchmark where we have a group of threads all trying to make updates to a shared hash table. So they pick randomly a key in the range 1 to 4096. They pick whether to update the table or whether to do a read-only access, just looking for a key. And they then just keep looping endlessly, and we time the number of operations that we can get. We time how long it takes each operation on the table on average. And the graph has 3 different versions of the hash table. The blue one going off to the top is showing what happens if we use coarse-grained locking. So we have one lock protecting the entire table. It's acquired by all of the operations on the table. We could do slightly better if we used a multi-reader single-writer lock, but that illustrates the kind of straightforward, easy-to-program case. And it quickly, you see, doesn't scale well because we're having to serialize all of the operations on the table. Now, the middle line is showing what we can do with fine-grained locking. So that's using a hash table where the designer has looked at it carefully. They've perhaps associated a separate lock with each of the buckets in the table so that threads that are doing work on items that hash to different buckets can work in parallel. And that scales really well for small numbers of CPUs where it's been particularly tuned for that workload. But the tuning has to be repeated for each of the different workloads that the hash table might be subject to. Perhaps with a large number of CPUs, we've got more contention for the buckets, and so some different locking strategy would be correct. Now, the lower line is showing what happens if we use atomic blocks and transactional memory. And what we can see here is that the time per operation scales really nicely as the number of CPUs increases, as the workload on the hash table gets more intense. And the reason for that is that no matter how many threads are working on the hash table, it's got a fairly large number of buckets, and there's going to be few conflicts for the actual memory accesses they want to make. So thinking back to that previous slide where the memory access is marked out on it in colored blocks, with this benchmark, there's going to be few times where concurrent threads have those blocks intersecting, where they're contending for access to the same memory. And so in most of the cases with atomic blocks, we can run threads entirely in parallel without any conflicts between them. Now, the downside for atomic blocks is if we zoom in on the bottom left of the graph, where the actual behavior for low numbers of CPUs is not going to be as good as a well-tuned locking design. And that's because we've got this extra step of logging all of the operations that the thread does as the atomic block executes, and the step at the end of the atomic block of reconciling those updates with the real state of the heap. So we've got extra overhead there to do the logging and to do the transaction commit. But the kind of overheads we're talking about are a factor of 2 slowdown on a benchmark like this when we're running on a single-threaded system. So in some settings, it's going to be an acceptable slowdown. And it's important to see that in this case, it's a benchmark that is always executing inside an atomic block. And so that's really the worst case. All of the memory accesses it's making are having to be logged. Whereas in a typical program, perhaps there's small sections that are atomic where one thread is interacting with the shared heap, and that large portions of the processing are done just directly, say on structures that are pulled out of a shared queue. So hopefully this is representing the kind of worst case performance for atomic blocks. And we've got some other research projects in the pipeline looking at what we can do to make it even faster on that left-hand end, where locking currently has a big performance win. But of course, we do have the software engineering benefits, the composability benefits that will be important in some settings beyond the simple performance comparisons that the graph is showing. So if you think through the kind of things that you might do in concurrent programs, you'll see that atomic blocks really, as I've described so far, are only a partial solution to these problems, because they can deal with atomic updates to a queue, taking an item off one end of it, but they don't provide a way so far of building richer data structures, where perhaps we want to wait until there's an item available in the queue and then take that. We'd have to fall back to locking and condition variables to deal with that. So an extension of this work that we've developed is to see what we can add to atomic blocks to make it possible to deal with that full range of concurrent programming tasks rather than just atomic transactional update to the heap. And the abstraction we've developed here is a new statement called retry. And that can be used in ways like the example here illustrates, where we want to do something to a shared data structure, and we discover that the data structure isn't yet in a state that lets us proceed. So in the example, we're calling the existing method on the queue to take an item from the left-hand end, and we now want to use that to build an operation that will block until there is an item on the left that we can take. So we try the operation we want. Maybe we get a null back from the queue saying that it doesn't have anything for us. We can then call this retry statement. And what retry means is that we're not yet ready to continue. So abandon what that atomic block has done so far, go back to the start of the block, and execute it again. So if you think about what would happen if we have this wait for left operation inside an atomic block, then if the queue is empty, we'll go through it, building up a log of all of the memory that we've accessed. We'll get to a retry if the queue is empty, and just throw away that log, go back to the start of the atomic block, and try again. Now that basic implementation would just be like a simple spin log. The thread would be there stuck, continually trying its work, continually finding that the queue is still empty until someone puts data into it. But the runtime system, because it's got this log of all of the data that the transaction has tried to access, is able to be smarter than just spinning. It can look at the transaction log and see all of the locations that the transaction has read from, and then interact with the scheduler to make sure that the thread isn't rescheduled until one of those transactions is updated, one of those locations is updated. So that means that we have a fairly simple programming model of just continually re-executing until we are able to get through the atomic block successfully without hitting retry. And we've also got an implementation that avoids spinning and avoids the kind of burning the CPU that would have. Something else to highlight from the software engineering viewpoint is that using retry and atomic blocks avoids another class of programming error. If you've used condition variables, then you've probably seen lost wake-up problems, where one thread wants to wake another, but some path through the code forgets to do a pulse or a pulse all on the condition variable. or maybe it does a pulse when it should have done a pulse all, and one of the threads is therefore not woken. This really pushes down the responsibility of matching up threads that do work that releases others from threads that want to block. It pushes that down into the runtime system, and so we don't have to worry about lost wake-up problems. In fact, there's more that can be done with retry. We have a second construct that allows a kind of choice between two operations that a thread might want to do. And so an example to have in mind here is perhaps that we have a server that has a number of queues that connect it to different clients, and we want to try to take an item from whichever of those queues has an item in it next. And we can do that by having an atomic block with two alternatives in it. We say attempt, first queue pop left, else second queue pop left. And what that attempt statement means is that we try the first alternative. If that goes through without hitting retry, then we're done. We fall through and go to process item. If the first alternative hits retry, then we try the second alternative instead. We try to go to the second queue and pop left. If that gets us an item, then we go and process it. And if neither of those gets an item, if both of them reach retry statements, then the thread blocks until either of the queues has data available in it. And so we're left waiting on either of those queues, and we'll pick up whichever of them next has data available. Now, what's particularly nice about this attempt statement is that we can actually compose it. If you think that the server has other tasks that it needs to be responsive to, say picking up shutdown requests, then we can take that main server loop that was dealing with Q1 and Q2 and wrap that in another attempt statement saying wait for shutdown request and then process the shutdown request. And if you programmed using abstractions like wait any operations on a group of handles, then you'll see that this really avoids one of the kind of boilerplate steps that's necessary with wait any, where you'd have to pull up all of the conditions that you want to wait on to some kind of top-level loop in the system, and then dispatch on a single call to that waiting operation. Here we can have waiting going on in one part of the system that's dealing with the actual queues that the server's interacting through, and then call that function from something else that's interested in waiting in a completely different condition. And we don't have to restructure the code to pull out the waiting to a single top-level loop. Okay, so I've got one final piece of work on concurrency to talk about this morning. And this is a kind of a higher level abstraction that we've developed for doing synchronization. And if you think back to those examples I've used with queues and different threads communicating through them, you'll see that it was still necessary to be fairly explicit about how the queue was being implemented. It was being implemented with objects, with links between them, and operations where we had to describe how the objects were manipulated, either using locks or using atomic sections. And that has those techniques have dealt with a lot of the problems that I talked about at the start of this session, to do with avoiding races, avoiding deadlocks, and to some extent getting scalability. But there's still one scalability bottleneck that exists with all of those systems, and that's that we can only have one thread at a time working on each end of the queue. If we have 1,000 threads trying to put data in and 1,000 threads trying to take data out, then those groups of threads have both got to line up. We put one item in, take it out, one item in, take it out. Whereas we'd really like to be able to match up all 1,000 of those threads at the same time. And if we've got enough processors to do the data transfers between the pairs of threads without having to serialize the data items if the queue has got the appropriate semantics. And this final abstraction I'll talk about provides one way of dealing with that kind of system. And as we'll see in a couple of examples, it provides a lot of other abstractions as well for structuring code where we've got complex waiting conditions between groups of threads. The abstraction here comes from a research language called C omega, and it adds two new abstractions to C#. The first of these is actual support in the language for asynchronous methods. So we document these by having async as part of the method signature. And then when a thread calls an async method, that call is allowed to be dispatched in a different thread from the one that the caller executed in. And that, of course, provides some benefits for concurrent programming, because if we have a large number of async calls and we have a large number of processors available, then if we're making calls onto async methods, then those can be split across the full number of processors in the machine that are available to this application. And conversely, if we have just a small-way multiprocessor or a uniprocessor, we can fall back to efficient single-threaded ordinary procedure calls for those async methods, so where we can get low overhead on the calls. Now, the more unusual abstraction that C omega adds is this structure at the bottom, which we call a chord. And the idea with a chord is that it's identifying a set of different methods, and the runtime system buffers up calls into these methods until there's someone ready to call every single one of the methods in the chord, and then the chord is said to play. The last person who makes a call into it actually executes the body of the chord. And that might seem like a strange abstraction to provide, but what it does in an example like this is let us define an asynchronous method for putting data into a buffer. So callers can put data into the buffer without having to wait for someone to be ready to take data out. And then in a chord, we can say that we want to pair together get operations and put operations on the buffer. And the implementation just transfers the string that was passed into put back to the caller to get. So that's probably the shortest piece of code I've seen for writing a shared buffer in a language like this, where we really push the responsibility for all of the buffering and for matching up get and put operations into the runtime system of C omega, and therefore possibly allow this matching up to go on in parallel and get better scalability than would be possible with an explicitly managed buffer. Now, another example of where C omega is valuable is where we have interactions between groups of threads. And I'm sure you've seen examples before where one thread wants to do some operation, then at some point in the future it needs a response from that. But in the meantime, it's got some other work that it can get on with. And we can express that kind of structure very easily using chords and using async methods in C omega. The final example for this is illustrating that in a setting where we have a client that is going to make two calls onto objects that export two services. Then service 1 and service 2 both have to make returns at some point, providing data back to the client. And the client has to pick up these items when they've both been returned to it and continue with its processing. And you can see that if we have 3 processors available, then we've got a good amount of work that can be done here. The client has a bit of work that it can continue with after making its invocations on the 2 services. The 2 services themselves can run in parallel, perhaps using techniques like atomic blocks to control the concurrency that might exist between them. And then the services issue their responses back to the client, and once both come in, the client can continue. Now, the way we could structure this in C omega is to define a class called service that's got an asynchronous method for requests, and that takes a callback, which is a delegate supplied by the caller, the client thread, that says what to do once the service has computed its result. So callers make invocations on a request method on the service, supplying a callback, and the callback itself is then an asynchronous method that the client has produced that is used to deliver the results. The 2 arrows going left to right on the example there. Now, looking at the client side of this, we first of all build up some kind of utility classes that are used for synchronizing the delivery of the results back to the client. So this utility class join2 has 2 async methods which are called via delegates when the first and the second responses come back from the 2 services. And it then has a join chord that combines a call to join from the mainline thread in the client with the two asynchronous calls that the services will have made when they deliver results. And the join method is very simple. It picks up two integer results that have come from the services, and it just plumbs those back through to output parameters that the client has supplied. The code at the bottom then looks at what the client does. It instantiates a join to and makes the two async invocations on the servers, passing in callbacks for the results delivery methods. And then it can go on, do other useful work in the meantime while the two services are still running. And then at a later stage, invoke the synchronous join method on the utility class at the top to pick up the two results when the servers have computed them. So there's a couple of things to take away from this. I think the main one is that it lets us, with fairly simple extensions to the language, express more clearly the relationship between the different pieces of code that the client and the services are running. We're able to say that these two service requests could execute in parallel if there are enough processors or enough cores in the machine to do that. And we can also say, here's some extra work that the client can also do usefully, if there are useful computational resources for executing it. And of course, if this is running on just a standard machine with only one processor, then we can still implement it efficiently using ordinary function call and return, rather than having to go to some kind of heavyweight mechanism for synchronization between threads in those cases where it isn't necessary. Okay, so just to wrap up this session, I've gone through three general areas where we've got research in MSR looking at future facilities for concurrency. The first one is testing today's programs using a tool like Racetrack to highlight bugs using the current abstractions. There's then in the slightly further out what we can add to languages to make it easier to use those kind of current abstractions. And then further out, looking at what we can add with atomic blocks and synchronization chords to really have more support in the language for concurrent programming. Now, we've got some other projects in MSR that are looking at lots of other sides of concurrency. And you'll notice that with the slight exception of async methods, these have all really been focused on a model of explicit threading, where the user or the programmer is responsible for identifying what tasks can run in parallel. We've got some other research that's looking at explicitly data parallel languages, and in a research language called Haskell, automatic identification of code that can run in parallel. Haskell is a particularly interesting language where it makes clear distinctions between where code can have side effects and interact with shared state. And so that provides a lot of opportunities for the runtime system to identify pieces of code that are useful to do in parallel, because it knows that, because they don't involve shared state, that it's safe to run any portion of that concurrently with any other portion. It's a kind of performance question rather than a correctness one, as it would be in a traditional imperative language. There's a lot of relevant talks at PDC. You may well have seen the two earlier concurrency talks. If not, then do watch the DVD recordings for those. There was a talk yesterday afternoon about system.transactions, and that really, I think, fits really nicely into the abstraction of atomic blocks and the availability of transactions as a single abstraction for controlling concurrency and for helping develop robust software. Just after this session, there's a talk by Herb Sutter on future directions in C++, and I know that some of the work he'll be talking about there will be thoughts about concurrency, and so do go to that session too. If you want to follow up any of the particular projects that I've talked about, then you're welcome to come up and talk to me during the remainder of PDC. I'll go down to the fundamentals track lounge, and you can find me there. Or you can follow up on the individual project websites. Racetrack in the Silicon Valley lab, prototypes available for download for Spec Sharp and for Chords. And then we have a number of prototypes for the work on atomic blocks and memory transactions that will let you experiment with that either in this research language called Haskell or as a kind of programming library for C# that runs on an unmodified CLR, but that has a it's a slightly more cumbersome syntax than the simple atomic blocks that I've talked about this morning. Okay, so thank you very much for your time and attention. I hope there's time to take a couple of questions now. Yeah.
Do you think that current CPU architectures are appropriate for future directions?
Two questions.
So the question is whether current CPU architectures are suitable for future directions in concurrency. And I think there's a lot more we can do with current architectures. I don't think they're dead quite yet. In my experience, when developing concurrent software like the implementation of atomic blocks, there's been a lot of really surprising performance characteristics that I've seen. So really coming down to the need to develop the software so that it doesn't introduce contention down through the memory hierarchy. I've really seen that the performance when shipping cache lines around between the processors has been key to developing algorithms that are highly performant. So I think there's some surprises and some new experience that has to get out into the broader community about how to program effectively for these architectures. But I don't think that I don't think they're at the end of the line just yet. Yeah.
Is it true that all of these features are targeted for the managed code?
So the question is whether these features are targeting managed code only. Now, I'm afraid I don't know in detail about all of the projects. I know that with Racetrack, that's really building on earlier work that some of that same team have done, where they were actually taking unmodified, unmanaged C code. So there's certainly scope for applying a lot of these techniques in unmanaged code. Exactly how these research projects will evolve going forwards, I'm not sure yet, though.
Is there any plans to implement some of this feature in the next version?
So the question is whether there's plans to implement some of these facilities in future product versions. I'm afraid I can't say any definite things about timescales there. With all of this work, we've had a lot of interesting discussions with people in product groups, and we're in a stage of wanting to think some more about these abstractions, think some more about what kind of applications might be written using them, whether these are in fact the right abstractions or whether there's more research to be done. But there's certainly ideas that we're keen to take forward and to continue experimenting and researching with.
Can you elaborate some more on the transaction and memory usage and the cache as to how they interact and how they interact?
So the question was about how the transactional memory and the data cache interact. The general way that the system is structured is that we try to make sure that if two transactions are logically not interfering, so if they don't access the same objects, or in another implementation, if they don't access the same fields, that they don't start to contend down through the memory system. So we try to make sure that if a transaction is read-only in the field accesses it makes, that it doesn't need to acquire any shared cache lines in exclusive mode. And so that's really key to the scalability results that I had. And similarly, we try to make sure that, say, the data structures for the shared of the private transaction logs are kept in memory that's going to remain thread private, so that log is available already in exclusive mode on the current processor, rather than needing costly cache line fetches. So the results there were taken on a very large multiprocessor machine, and one of the key insights we got during the implementation was that we could do a whole lot of processing in the time that it takes just a single three-way cache miss to be serviced. And so that's one of the key things to think about as we look at implementations of this. Yeah.
What voltage
The question was about what tools we use to look at the performance of the memory system there. Actually, I did it in the low-level way of running the code and just thinking through the memory accesses that it was making. It would be great sometime to actually go back and check with more functional tools about whether there's other performance bottlenecks left in the system.
Is the implementation of some of these libraries actually using locking internally, like walking through the structures and queuing up recording in Omega?
So the question is whether we use locking internally in the implementations here. The implementation of atomic blocks builds just over interlocked compare exchange and read and write. I believe the current implementation of C omega does use explicit queues under the hood. It will be future work looking at some of the scalability work that could be used to drop in there in place of it. But at least the locking is pushed into the runtime system and not exposed to the programmer, and so we can look at a whole range of queues and dispatch methods for matching up the different methods on a chord. Okay, thank you very much.